Hello, and welcome to video 4, which is all about how to interpret the slope and the y-intercept of a regression equation in the context of the problem. So the nice thing about the equations of regression lines, like the least squares regression line, is that they actually represent real-life situations. So this means that the slope and the y-intercept are going to have contextual meaning. They're going to mean something in the context of our problem. So we know that the equation of our regression line takes this form. Y hat is equal to a plus bx. X and y are our variables, our explanatory and our response variables, and a and b are constants. This is just the equation of a line. You already know that this a term right here is the y-intercept. In context, the y-intercept is the predicted y value when x is equal to 0. Sometimes this is going to make sense in the context of our problem, and sometimes it'll be an extrapolation. I'll show you examples of both. The other constant, b, is our slope. You already know that slope is the change in y over the change in x. So in context, when x increases by 1, we expect y to increase by whatever the slope is, b, on average. So again, when x increases by 1, we expect y to increase by the slope on average. These facts have always been true, okay? These properties are true for any line. It's just that in statistics, they usually have context. Let's start by looking at the y-intercept. In y equals 2 plus 4x, the y-intercept is 2. And if you look at the graph of our line, what that means is when x is equal to 0, y is equal to 2. Again, when we're in statistics, we're going to put this in context. Let's look at the slope as well. The slope is 4. So that means as x increases by 1, y increases by 4. When I go over 1, this line goes up 1, 2, 3, 4. So the slope is when x increases by 1, we expect y to increase by 4. So here is our first example that we're going to do in context. It says, let's say that we can use the following least squares regression line to predict a husband's age given his wife's age. And it says y hat is equal to 1.267 plus 1.58x. And it tells us y is the husband's age, so that's our response variable, and x is the wife's age, which is the explanatory variable. And we're told to interpret the slope and the y-intercept. So we're going to start with slope, and I've given you sort of a format for how you should put your answer. And it says as x increases by 1, and then tell me what the units are, we expect y to increase by whatever the slope is on average. Except you're not going to say x and y, you're going to tell me what x and y are in context. So let's fill in the blanks. As x increases by 1, so x is the wife's age, so as the wife's age increases by 1, let's say this is in years, by 1 year, we expect y, which is the husband's age, to increase by, and then what's the slope here? 1.58, and then the units for y, years, on average. So if we're comparing two couples, if the wife is 1 year older, we'd expect the husband to be 1.58 years older on average. Now, using this same example, we're going to interpret the y-intercept in context. So I kind of gave you the format for how you should put your answers here. And I said when x is 0 units, we predict y to be the y-intercept on average. And again, you're going to put this in context. So when X, and X is the wife's age, is 0 years, we expect Y, which is the husband's age, to be, and then what's the y-intercept? 1.267 years on average. Now let's step back and see if this makes sense. Your slope should always make sense, but your y-intercept won't always. When the wife is 0 years old, we expect the husband to be 1.267 years old. That doesn't really make sense. People don't get married quite that young. So this would probably be an extrapolation. It does not make sense. So here is another example. This comes from a study on obesity. Some researchers wanted to find out why some people don't gain weight even when they are overeating. And they thought maybe fidgeting and other non-exercising activity might explain why. Some people may spontaneously increase their non-exercising activity when they're fed more. And that just means fidgeting, just sort of little non-exercising movements that you do during the day. So the researchers deliberately overfed 16 healthy young adults for 8 weeks, and they measured fat gain in kilograms, and as their explanatory variable, they measured the change in energy use from activities other than exercise. So this is the least squares regression line that they came up with. They have fat gain is equal to 3.505 minus 0.00344 times their change in non-exercising activity. And go ahead and pause this video and try to interpret the slope of this regression line. Okay, let's see how you did with the slope. So I said as X, which is my NEA change, increases by 1, and I didn't give you the units, sorry, it's calories. So as the NEA change increases by 1 calorie, we expect fat gain to decrease. Now think about why this is a decrease. It's because my slope is negative. So as X increases, Y is actually decreasing. We expect fat gain to decrease by 0.00344 kilograms on average. Now I want you to do the same thing, but with the y-intercept. So please pause the video and interpret the y-intercept of this least squares regression line in the context of the problem. Okay, let's see how you did with the y-intercept. I said when the NEA change, when X is 0 calories, we predict that the fat gain will be, and what's the y-intercept? 3.505 kilograms on average. Now I want you to ask yourself if this y-intercept makes sense. I think it does. If a person doesn't change how much non-exercising activity they're getting, but they're being overfed, we predict that they're going to gain 3.505 kilograms of fat on average. That makes sense. Okay, we're going to do one more example. This is a least squares regression line that describes the relationship between someone's shoe size, X, and their height in inches, Y. So we're looking to see if we can predict someone's height from their shoe size. And I want you to pause the video and interpret the slope and the y-intercept in the context of this problem. Okay, let's see how you did. For slope, I said when the shoe size increases by 1, and I think the units are implied with shoe size. So when shoe size increases by 1, we expect height to increase by 1.65 inches, and I'm a bad teacher because I forgot on average. Okay, let's look at y-intercept. I said when someone's shoe size is 0, we predict their height to be 53.24 inches on average. Does this make sense? No, this would be an extrapolation. We don't expect to have any data that's close to a shoe size of 0. So this is using the line to make a prediction that's out of the range of the data. Okay, this is the end of video 4. Please answer the questions that follow and come to class prepared to discuss this. Thank you.